Usually when we talk about a medical diagnosis, there's this expectation of absolute precision. You break your arm, the x-ray shows that jagged white line, and the doctor just points at the screen and says, there it is.
Yeah, it's incredibly binary.
Right. It's binary. Broken or not broken.
It's comforting in a way, I think.
Yeah.
We like the world to be visible, to be neatly categorized, and just immediately understandable.
Exactly. But then you step into the world of everyday manufactured objects, and suddenly that x-ray machine just completely fails us.
Oh, totally.
We're looking at a landscape of creation that is entirely invisible to most of us. Like if you look at the cereal box sitting on your breakfast table right now, or a glossy magazine on a newsstand, or, even a piece of junk mail you just pulled out of your mailbox.
Right, the stuff we just throw away.
Yeah, there is an entire highly specific, almost secretive vocabulary behind its creation that we simply never see.
It really is a totally hidden architecture. The physical world of media is built on a very rigid, highly evolved industrial language. And if you aren't initiated into that industry, it just looks like, a cereal box.
Yeah.
You see the surface, but you don't see the structural engineering, the chemistry, or the sheer mathematical precision that's actually holding it together.
And so that is our mission for this deep dive. We are going to put on those x-ray glasses today.
I love it.
We are taking an incredibly comprehensive glossary of terms pulled straight from the Graphic Design Reference Plus specification book, and we are going to use it to trace the entire unbroken life cycle of a design project.
Right. We are going to take you from a completely blank sheet of paper all the way to the final printed physical piece arriving in your hands.
Which is quite a journey.
It is. And we are going to unpack the exact language that graphic designers and commercial printers use to force abstract ideas into physical reality.
Which is honestly the coolest part to me. Just how an idea in someone's head survives the heavy, messy, violent world of industrial manufacturing.
Oh, it gets very violent.
It does. Now, before we jump in, if you love uncovering the hidden mechanics of how the world is actually made, make sure you hit that subscribe button on the channel.
Highly recommend it.
And if you want to own a physical copy of this incredible design Bible we're exploring today, you can simply scan the QR code right there on your screen, or, you can find the book link directly below in the description. It is an absolute must-have for anyone who wants to understand visual communication.
Yeah, it's basically the skeleton key for the entire industry.
All right, so let's start at zero. Every great piece of design has to start somewhere in the physical universe, right?
Right.
Before you have typography, before you have color or ink, you must have a canvas.
Exactly. You have to decide what physical substrate is actually going to carry your message. If the paper is wrong, every single decision you make afterward is compromised.
I always think of it like pouring the foundation of a house.
That's a great way to look at it.
Right, because if you are designing a luxury mansion, you don't pour the same shallow foundation you'd use for a temporary garden shed. The paper you choose dictates the structural integrity of the whole project.
That is the perfect analogy.
Yeah.
And the terminology used to define that foundation is incredibly precise, but also surprisingly globally divided.
Oh, of course it is.
Yeah. Let's look at dimensions and standards first. So globally, almost everywhere except North America, paper size is dictated by the ISO standards.
Okay.
This is the A-sheets, B-sheets, and C sizes.
The metric system approach, basically.
Exactly. And the geometry behind it is beautiful. Like an A sheet of paper has an area of exactly 1 square meter.
Wow. Okay.
But its aspect ratio is 1 to the square root of 2. And why does that matter? Because if you fold an A sheet perfectly in half, you get an A1 sheet, which has the exact same proportions.
Oh, I see.
Yeah. Fold it in half again, you get A2. The proportions never distort, no matter how small you cut it.
So a designer can scale a layout up or down flawlessly without having to, redesign the margins every single time.
Precisely. And B sheets use that exact same geometric logic, but are slightly larger than A sheets, which are often used for printing presses. So you have room to actually grip the paper before trimming it down to an A size.
Nerd.
And then C sizes are specifically dimensioned to create envelopes. So an A4 letter fits perfectly with absolute mathematical precision into a C4 envelope.
That is just so elegant. But of course, here in the US and Canada, we don't do elegant. We have our own system.
We certainly do. And it gets incredibly confusing when we talk about weight and measurement.
Oh boy.
So in the ISO system, weight is measured by grammage. It is blissfully simple. It's the weight in grams of a single square meter of that specific paper.
Right.
It's expressed as gramism, or grams per square meter.
Mhm.
A higher gramism number always means a heavier, thicker paper.
Okay, simple enough. But the North American system uses basis weight, and I have to admit the logic here feels like it was invented by a bad man. It's measured in pounds per ream, right?
Yes, it is. Basis weight is the weight in pounds of one ream of paper. And a ream is exactly 500 sheets.
So if I buy 50-pound paper, a stack of 500 sheets weighs 50 pounds.
Well, only if those sheets are cut to their basic size, and this is where the madness sets in.
Uh-oh.
Different categories of paper have completely different historical master sizes before they are cut down for the consumer.
Wait, so a master sheet of one type of paper is physically larger than a master sheet of another type?
Exactly. The basic size of the bond paper is 17 by 22 inches. But the basic size of a cover stock is 20 by 26 inches.
You're kidding.
Nope. So 50 pounds of bond paper and 50 pounds of cover stock feel completely different in your hand because you are weighing 500 sheets of entirely different physical dimensions.
That is wild. It means a 50-pound cover stock is actually much thicker and denser than a 50-pound text stock because the 50 pounds of cover stock is distributed over a smaller total surface area in its master size.
You've got it. It's a historical quirk from the 1800s that the industry just never bothered to abandon.
That's hilarious.
Right. And if a paper gets so thick that weighing it becomes impractical, like heavy cardboard for packaging, they just stop using weight entirely and switch to point.
Point being a physical measurement of thickness, not weight.
Right. A point is 1/1000th of an inch. So a 14-point cardstock is exactly 0.014 inches thick. It's how you measure structural rigidity.
Okay, so we've established how to measure it, but what are the actual materials we're measuring? Because the industry categorizes everything into grades.
Yes.
You have graphic arts papers, which are engineered specifically for high-quality commercial printing, versus industrial papers.
And industrial papers are really the unsung heroes of the physical world. Think about craft paper.
Okay.
It's a highly durable paper made from unbleached wood pulp. The word actually comes from the German word for strength. It's your classic brown paper grocery bag.
Or chipboard, right. Which is essentially solid recycled cardboard used in packaging or as the rigid core of a hardcover book. And you would never try to run chipboard through a high-end printing press to reproduce a fine art photograph. It would destroy the machine and look terrible.
Yeah, that would be a disaster.
Yeah.
But if you are printing a photograph or a brochure, you move to the graphic arts grades. And the most ubiquitous is bond paper.
That's the stuff sitting in my home printer right now, isn't it?
Exactly. It's the workhorse. It was originally made for printing government bonds, hence the name, but now it's the standard for letterheads, photocopiers, and just everyday correspondence.
Right.
It's relatively lightweight and engineered to absorb pen ink and copier toner quickly without smudging.
If we're printing a book, though, we need something a bit more refined, which brings us to text paper. It falls right in the middle, right? Like heavier and higher quality than bond, but not as stiff as a cover.
Yeah, precisely. And what wraps around that text paper, cover stock, it has a significantly heavier basis weight
Makes sense.
because it has to endure the physical friction of being handled, pulled on and off shelves, and protecting the fragile text pages inside.
And if you need something that essentially stands up on its own, like a postcard or a heavy file folder.
You specify Bristol. Bristol is a broad term for heavy stock, usually 6 points or thicker.
Gotcha.
Or you might use paperboard, which is sometimes called board paper. That's heavy index or cover stock, used almost exclusively for folding cartons. When you grab that cereal box, you are holding paperboard.
Okay, let's say we are designing an ultra-high-end corporate annual report. We have our foundation, but we need it to look and feel expensive. We have to look closely at the physical characteristics of the paper surface.
Oh, absolutely.
First up is brightness.
Right, and brightness is a literal scientific measurement of light reflectivity. It calculates the specific percentage of blue light that a sheet of paper reflects back to the viewer's eye.
Why does that matter for printing, though? Like, practically?
Because printing ink is translucent. When ambient light hits a printed page, it actually travels through the layer of ink, bounces off the paper underneath, and travels back through the ink to your eye.
Wow, I never thought of it like that.
Yeah. So the brighter the paper, the more light bounces back, and the more vibrant and explosive your printed colors appear.
But if the paper is too bright and thin, we run into the issue of opacity.
Yes. Opacity is the paper's ability to block light from passing all the way through to the other side.
Which is crucial.
Very. Because if you are printing a double-sided annual report, and your opacity is too low, the text from page 2 is going to show through as a muddy, distracting shadow on page 1.
Now, this next concept completely blew my mind regarding how paper is actually manufactured, the physical texture or the finish of the paper.
It's fascinating.
We all know you can buy textured paper like linen, laid, vellum, but every single sheet of paper naturally has two completely different sides. The felt side and the wire side. How is that even possible?
It all comes down to the sheer physics of the massive fourdrinier machines used in paper mills.
Okay.
Paper doesn't start as a solid. It starts as a wet, flowing slurry of 99% water and 1% wood pulp. This slurry is sprayed onto a rapidly moving, continuous wire mesh belt.
So gravity pulls the water down through the mesh.
Exactly. The side of the slurry that sits directly against that metal mesh, the bottom, is permanently imprinted with the microscopic pattern of the wire.
Oh.
That is the wire side, and it is inherently rougher.
And the top side?
The top side is exposed to the air and eventually comes into contact with heavy woolen or synthetic felt rollers that press the remaining water out. That side is the felt side.
That makes so much sense.
Because it's pressed flat rather than draining through a mesh, the felt side is much smoother and generally preferred for high detail printing.
So an ordinary piece of paper has a distinct top and bottom. That is incredible. Though, I guess to avoid that difference, manufacturers often apply coatings, leading to the massive divide between uncoated paper and coated paper.
Uncoated paper is exactly what it sounds like. It's the raw, porous wood fiber. It has a tactile, organic feel to it. When wet ink hits it, the paper absorbs it like a sponge.
Which means the ink spreads out slightly, so you can't print ultra-crisp microscopic details.
Right. If you want photographic precision, you must use coated paper. In the mill, the paper is coated with a microscopic layer of clay and binders.
Clay.
Yes, clay. This fills in all the microscopic valleys between the wood fibers, creating a sealed, completely flat surface.
So the ink sits perfectly on top of the clay rather than soaking into the wood.
Exactly. And you can manipulate that coating. You can have a matte or dull finish, which is a flat, non-reflective coating. It's very sophisticated, very easy to read text on because there's no glare.
Or you can go the opposite extreme with cast-coated paper.
Oh, yeah.
This is a high-gloss finish created by taking the paper while the clay coating is still wet and pressing it aggressively against a highly polished, heated, chrome-plated metal drum. It bakes the clay into a literal mirror finish.
You can also achieve a smooth finish without clay by using a process called supercalendered.
I love that word. It sounds like a superpower.
It essentially is a superpower of pressure. The raw paper is forced through a towering stack of alternating heavy steel and hard fiber rollers called a calender. The sheer, massive physical pressure crushes the wood fibers completely flat, polishing the surface through friction. It creates a smooth, glossy finish without adding any clay. Magazines often use supercalendered paper because it's lighter to mail than clay-coated paper.
Sometimes a designer wants to show off the manufacturing process itself, like incorporating a watermark. You hold a piece of high-end stationery up to the light, and you see a translucent logo or crest embedded right inside the paper.
That's actually done while the paper is still mostly water on that wire mesh. A wire cylinder with a raised design rolls over the wet pulp, physically displacing some of the fibers.
So it's literally thinner there.
Yes, it literally makes the paper slightly thinner in the shape of the logo, which is why more light passes through it.
You also see high-end art prints or wedding invitations with a decal edge. It's this feathery, ragged edge on the paper.
Historically, the decal was the wooden frame that contained the wet pulp when making paper by hand. Pulp would inevitably seep under the frame, creating that ragged edge. Today, it's simulated by a localized water jet cutting the paper on the machine. It's an intentional imperfection that signals luxury and bespoke craftsmanship.
Okay, so we have all these gorgeous options, but we really can't ignore the environmental reality of this industry.
No, we can't.
Graphic designers are constantly weighing the aesthetic of their foundation against its ecological impact. The terminology here is an absolute alphabet soup.
It is a critical, ethical, and practical specification. You have to know the origin of your canvas. The baseline is virgin fiber. This is paper pulp derived directly from freshly cut raw timber.
And the cardinal rule is that you do not want your virgin fiber sourced from old growth or intact forests.
Never.
These are naturally occurring forests that have been allowed to grow undisturbed for over 100 years. They are irreplaceable ecosystems.
So the alternative is recycled paper. But the industry divides this into two very distinct categories: pre-consumer and post-consumer.
Pre-consumer waste is basically manufacturing efficiency, right? It's the trimmings, the scraps, the defective sheets that happen inside the paper mill or the printing plant.
Right.
They just sweep it up, throw it back in the vat, and make new paper. It's great, but it never actually lived a life out in the world.
Correct. When you want to pull waste out of the global landfill system, you specify post-consumer waste. This is a cereal box that went to a grocery store, went to a family's breakfast table, went into a recycling bin, and was physically collected, sorted, and broken down to make new paper.
And to make that post-consumer waste usable again, it has to go through de-inking. A massive industrial process of washing and floating the paper pulp in chemicals to strip away the old ink, varnishes, and glues.
Now, what if you want to avoid wood entirely? You look for tree-free paper. But even here, there are nuances. You have agricultural residues.
I think this is such a smart concept. These are fibers recovered from crops planted primarily for food, like wheat, corn, or sugarcane. They harvest the food for human consumption, and instead of burning the leftover stalks, they pulp them to make paper.
It's a perfect secondary use of the plant. Contrast that with agricultural fibers, which are crops grown specifically and solely to be turned into paper, like hemp or kenaf.
Okay, so whether it's wood or wheat, the raw pulp is naturally brown. To get that high brightness we talked about earlier, it has to be bleached. And historically, the printing industry used raw chlorine.
Elemental chlorine is phenomenal in stripping away lignin, the natural glue, holding the plant fibers together and turning paper pure white. But the problem is that elemental chlorine bonds with organic matter to create dioxins, which are some of the most toxic, carcinogenic pollutants on Earth, and they were being dumped directly into waterways.
Which led to the creation of strict environmental bleaching labels. First is ECF, elemental chlorine free.
This means the mill didn't use pure elemental chlorine gas. Instead, they used chlorine derivatives, like chlorine dioxide. It drastically reduces dioxin production, but, it's still a chemical process.
Then there is PCF, processed chlorine free. This one is tricky.
It is. PCF applies to recycled paper. It guarantees that no chlorine whatsoever was used during the recycling and de-inking process.
Okay.
However, because it's made of old paper, that original paper might have been bleached with chlorine a decade ago when it was first made.
Oh, wow. And the absolute gold standard, TCF, totally chlorine-free.
This means the virgin paper was bleached using entirely benign agents like oxygen, ozone, or hydrogen peroxide. No chlorine in any form ever touched the fiber.
All of this specification matters because the print industry operates on a massive scale. We have to be mindful of carbon dioxide emissions from logging and transport and VOCs, volatile organic compounds.
VOCs are carbon-based chemicals that evaporate at room temperature. In printing, they come from petroleum-based inks and cleaning solvents.
Right.
When VOCs hit the atmosphere and react with sunlight, they create ground-level ozone, which is smog. Choosing the right paper and eventually the right soy-based inks is how a designer mitigates that footprint.
We will definitely get into ink and waste like spoilage, the paper inevitably destroyed during the press setup when we hit the press room. But for now, we have made our choices. We have our perfectly flat, sustainably sourced, totally chlorine-free coated foundation.
The canvas is ready.
But a blank canvas isn't a message. It's time to build the architecture of the page.
If the paper is the concrete foundation, the layout is the structural framing of the house. You cannot start hanging drywall, putting in text and photos until the studs are perfectly aligned.
And the fundamental framing tool is the grid. It is an invisible underlying geometric framework that dictates absolutely everything on the page.
The grid brings order to chaos. It ensures that a 200-page book feels cohesive.
A key part of that grid are flow lines, sometimes called thresholds. These are horizontal divisions across the page that create alignment points. So every chapter title drops down to the exact same flow line, creating a consistent rhythm for the reader.
And you must establish your boundaries. That is in margin, the negative white space at the top, bottom, and sides of the page.
Right.
Margins aren't just empty space. They are a psychological breathing room for the eye and a physical place for the reader's thumbs to hold the book without covering the text.
Inside those margins, we build the column, vertical blocks that constrain the width of the text. Because if a line of text runs all the way across a wide page, the human eye physically struggles to track back to the beginning of the next line. Columns make reading effortless.
And separating those columns is the gutter. This is the vertical strip of white space between columns. But more importantly, the gutter is the central fold between two facing pages in a bound publication.
To give the text gravity within those columns, designers use a baseline, a continuous, invisible horizontal line that the bottom of every letter sits on. It locks the text into the grid.
Once the grid is built, we have to make decisions about arrangement. How are we placing elements?
We might make the text flush. This means the text is aligned perfectly flat against the left or right margin, creating a hard, crisp, vertical edge.
We also look at the overall balance. We can use symmetry, where elements on the left side of the page perfectly mirror elements on the right. It feels incredibly formal, stable, and traditional. Think of a wedding invitation.
Or we disrupt that with asymmetry, placing a massive, heavy photograph on the bottom left and balancing it with a tiny, dense block of text on the top right. It isn't mirrored, but it creates visual tension and a modern dynamic energy.
When positioning multiple elements, a designer might decide to butt them, to join two photos or color blocks absolutely edge to edge with zero space between them.
But what if you want a photograph to explode off the page? You want it to go all the way to the absolute physical edge of the paper with no margin at all. That is called a bleed.
Bleeds are visually stunning, but they create a major manufacturing problem.
Oh, I bet.
A commercial printing press physically cannot print ink all the way to the very edge of a sheet of paper. If it tries, the ink slocks over the side and completely coats the internal cylinders of the machine in a sticky mess.
So how do you do it?
You fake it. To create a bleed, the designer prints the image on a piece of paper that is significantly larger than the final desired size. The image actually prints past where the edge will eventually be. Then a massive guillotine blade comes down and physically chops off the unprinted edges, slicing right through the wet ink.
You print past the finish line and then chop off the excess.
Exactly.
Usually a bleed extends about 1/8 of an inch past the cut line. To tell the bindery exactly where to drop that blade, the designer places crop marks or trim marks on the file.
These are tiny crosshairs, and it is absolutely critical that crop marks are placed outside of the final image area, because if you put them inside the trim area,
They'll end up printed on the final product and you've ruined the job.
yes,
Now, there is one type of bleed that causes printers to wake up in cold sweats, the crossover, also known as a gutter bleed.
this is when a single continuous printed area, like a massive landscape photograph, starts on the left page, crosses straight over the center gutter, and continues onto the right page.
The precision required here is terrifying. Imagine a crossover photograph of a person's face. One eye is on page 24, the other eye is on page 25. Those two pages might be printed on completely different pieces of paper at different times and then bound together. If the machine folding the paper is off by 1 single millimeter,
The person's face is fractured. The eyes don't line up. The illusion is totally shattered. Crossovers require an incredibly deep understanding of how the bindery operates.
Okay, the framing is up. Let's look at the anatomy of the content we're placing. The vast majority of the text is the body copy, or just text. The heavy blocks of paragraphs intended for sustained reading.
Above that, drawing the eye, is the headline. Set in large, bold type, its entire job is to arrest the reader's attention and force them into the body copy.
Sometimes a headline uses display type. This isn't just a bigger version of the body copy. Display type is highly stylized. It conveys an emotional mood or a brand identity.
Right.
You would never use it for a dense paragraph because it's too elaborate to read for more than a few words.
If we place an image on our grid, we anchor it with a caption, also known in the newspaper industry as a cut line. A brief sentence physically close to the image that contextualizes or identifies what the reader is looking at.
To help the reader navigate the physical object, we use a folio. Typically sitting at the bottom of the page, the folio contains the page number, maybe the chapter title, or the issue date.
And on the cover of a magazine, the most crucial architectural element is the masthead, the uniquely designed, recognizable name of the publication. Though, confusingly, masthead is also used to describe the small box inside the magazine listing the publisher, editors, and staff credits.
So that is the macro architecture. But the real obsession of graphic design happens on the micro level, the typography itself.
The fundamental building block is the character. Every individual letter, numeral, comma, and symbol on your keyboard is a unique character.
Now, we need to clear up the most common fundamental misunderstanding in all of design: the difference between a typeface and a font. People use them interchangeably, but they are completely different concepts.
They are. Let's define typeface. A typeface is the pure, abstract design of the characters. It is the visual concept, the specific shapes of the curves, the thickness of the lines, the artistic DNA unified across an alphabet. Helvetica, Garamond, Times New Roman, those are the names of typefaces.
Okay, so if the typeface is the artistic idea, what is a font?
A font is the delivery mechanism. It is the physical equipment or the digital software file that enables a machine to actually reproduce that typeface.
I love this distinction. So Helvetica is the typeface, the idea of what the letters should look like. But the OTF file that I install on my MacBook so my screen can generate Helvetica, that piece of software is the font.
Exactly. In the days of metal type, the typeface was the design drawn on paper, and the font was the heavy wooden drawer full of lead blocks carved into those shapes.
That makes perfect sense. Now, a single typeface usually comes as a type family, a complete range of style variations built around that core design DNA.
Within that family, you have type styles. These are structural modifications that give a designer variety while keeping the visual harmony intact. You alter the weight, using boldface to make the characters darker and thicker for emphasis.
You can alter the width. A condensed type squishes the characters horizontally, allowing you to fit a long headline into a narrow column. An extended typeface stretches them out horizontally, creating a very wide cinematic feel.
You can alter the angle using italic. Characters slanted to the right, historically designed to mimic fast handwriting, used to emphasize a specific word within a block of upright text.
And you can alter the case, using small caps. These are capital letters that are intentionally drawn to be the exact same height as the lowercase letters in the sentence. It's incredibly useful for acronyms like NASA or FBI.
Oh, absolutely.
If you use full-size capitals in the middle of a paragraph, they look huge and distracting. Small caps blend right in.
And if you look closely at the anatomy of these characters, they have specific features, like a descender. This is the specific part of a lowercase letter, like the tail of a G, J, P, or Y, that physically drops below that invisible baseline we talked about earlier.
Choosing the typeface is only half the battle. A typesetter's real job is managing the negative space between those characters. Which brings us to kerning.
Ah, kerning.
Bad kerning is an invisible crime. I always compare it to a living room where the furniture is arranged just slightly wrong, so every time you walk through, you bump your shins on the coffee table. You can't always articulate why it's wrong, but your brain feels the friction.
Kerning is the microscopic adjustment of space between two specific letters. Because letters have irregular shapes, setting them mathematically equal distances apart creates terrible optical illusions. A capital W next to a lowercase a creates a massive, ugly gap of white space.
Right.
Kerning allows the designer to physically slide the A over so it tucks neatly under the angled arm of the W. It creates visual harmony.
But if you want to adjust the spacing of a whole word, not just two letters, you use letter spacing, which designers today usually call tracking. You select an entire headline and uniformly expand the distance between every single letter to make it feel airy, or tighten it up to make it feel dense.
And to control the vertical space between lines of text, you use leading.
Which is another amazing historical ghost in the machine. Why is the space between lines of text on a computer called leading?
Because for hundreds of years, to push lines of metal type further apart, a printer had to physically insert thin strips of raw lead metal between the rows of letters in the press. The computer still uses the terminology of heavy metal.
If that leading and tracking isn't managed perfectly, the text flow breaks and you end up with a widow.
A widow is a typographic tragedy. It's a single, lonely word or part of a hyphenated word that ends up on the very last line of a paragraph all by itself. Or worse, it gets pushed to the very top of the next page. It creates a massive jarring hole of white space. Designers will spend hours tweaking kerning and tracking just to pull that single word back up, or push more words down to keep it company.
To break up these blocks of text, a designer might drop in a rule. This is simply a horizontal or vertical line of any thickness used to divide sections or frame content.
Or for a massive visual impact, they might employ a reverse.
This is a great trick. Instead of printing black text onto white paper, you draw a massive black box and you make the text white. But there is no white ink on a standard press, so the printer floods the box with black ink but leaves the shapes of the letters completely blank, allowing the raw, unprinted white paper to show through. The paper itself becomes the typography.
And finally, as the designer and editor review this architecture, they use specific proofing marks. If an editor crosses out a sentence, but then realizes they made a mistake and wants to keep it exactly as it originally was, they write "stet" next to it.
Stet, Latin for let it stand. It means ignore the correction, the original architecture was correct.
So we have built our framing. We have our margins, our beautifully kerned typography, our image boxes. But today, all of this architecture exists entirely as glowing light on a computer screen.
Which means we have a massive translation problem. We have to convert everything we just designed for human eyes into a digital language that a heavy manufacturing machine can understand. We are entering the digital realm.
This is the pre-press bridge, and we have to categorize the digital assets we are working with. Generically, we call them images, any visual counterpart of an object or scene, but digitally, they are processed in fundamentally different ways.
The biggest divide is between continuous tone and line art. A continuous tone image is a standard photograph. It has smooth, fluid transitions of color, a pale sky blending seamlessly into a dark mountain. There are millions of shades of gray or color.
But a printing press cannot print a fluid transition. It can only print solid ink. So if you don't have a photograph, you might use line art, also called line copy.
Right.
This is an image that is purely binary, 100% black ink or 100% white paper. There are no grays, no shading. Think of a sharp pen and ink illustration or a barcode.
If you have a physical piece of line art, you have reflective art, or hard copy. It's an object that relies on light bouncing off it to be seen. To get it into the digital realm, you run it through a scanner, which bounces light off the paper and translates the reflections into digital data.
If that reflective art is just a typed document, you don't want a picture of the paper. You use OCR, optical character recognition. The software analyzes the scanned image, recognizes the shapes of the letters, and converts them into editable, searchable text data.
Once the assets are digitized, they are saved in specific file formats. The most basic is the native file format. If you create a layout in Adobe InDesign, the INDD file is the native format. It preserves all your layers and history, but you can't just send that to anyone unless they also own InDesign to translate it.
When it comes to the images inside that layout, the computer processes them in one of two ways, as a bitmap or as a vector.
This is the most important concept in digital design. A bitmap is a photograph. It is a rigid grid of millions of microscopic colored square pixels. If you take a bitmap image of a baseball and zoom in 500%, the illusion breaks. You don't see a curve anymore. You see a jagged staircase of square blocks.
Because a bitmap has a fixed amount of data.
Right.
If you try to blow it up to the size of a billboard, the computer just makes those square pixels larger, and the image becomes a blurry, blocky mess.
But a vector graphic is practically magic. It doesn't use pixels at all. It uses mathematical equations.
Yes. A vector file doesn't say put a black square here and a gray square here. It says draw a curve from coordinate A to coordinate B with a specific arc radius and fill it with black.
Because it's just pure math, vector graphics are infinitely scalable. You can take a vector logo that is 1 inch wide on your screen and scale it up to cover the side of a 50-story building, and the edges will remain microscopically, mathematically perfect.
To save these vectors and bitmaps, we use a litany of file extensions. You might save your vector logo as an EPS, encapsulated PostScript. This is a robust format specifically designed to place scalable graphics into larger documents.
For bitmaps, you have JPEG, created by the Joint Photographic Experts Group. JPEGs are tiny files, perfect for websites because they use lossy compression. They permanently delete data to save space.
Which is why you should almost never use a JPEG for high-end print. The printing press will aggressively magnify the digital artifacts created by that lost data. For print, you want a TIFF tagged image file format. It preserves every single pixel of data perfectly.
There are older formats too, like PICT for early Macintoshes or GIF, an 8-bit format that only holds 256 colors used for simple web animations.
But the undisputed king of sending your final finished layout to the printer is the PDF portable document format. It bundles your vectors, your bitmaps, and your fonts into a single locked file that will open and look identical on any computer, regardless of what software they have installed.
Now, if you are using bitmapped images, photographs, you live and die by resolution. This is the density of the pixel grid, measured in dpi, dots per inch.
The math here is unforgiving. If you want a crisp print, you need a high-res image, which generally means 300 dpi at the physical size it will be printed. A 100 dpi low-res image looks fine on a computer monitor, but will print like a muddy, jagged disaster.
This creates a major workflow hurdle. If you are designing a 300-page clothing catalog with thousands of ultra-high-res TIFF files, the sheer amount of data will cause your computer to crash every time you try to scroll down the page.
To survive, designers use an FPO for position only.
I always call these stunt doubles. You take the massive 100-megabyte high-res image, and you generate a tiny, low-res 1 megabyte copy. You place that low-res stunt double into your layout. It looks a bit fuzzy, but it allows you to quickly crop, size, and arrange the page without crashing your computer.
It does all the exhausting rehearsal work. But right before the final file is sent to the printer, the software automatically swaps out the low-res stunt doubles and links back to the original high-res actors for the final performance.
The fonts also have stunt doubles. The computer uses a screen font, which is optimized to look smooth on a glowing monitor made of square pixels, but sends a printer font file to the press, which contains the exact mathematical vector curves needed to etch the metal plates.
But the most mind-bending translation that has to happen between the screen and the physical paper is color. We're dealing with two completely incompatible physics of light.
On your monitor, you are designing in RGB, red, green, and blue. This is additive color. Your screen is literally a flashlight shooting photons directly into your retinas.
When you turn off the red, green, and blue pixels, you get black, the dark screen. If you turn them all on at 100% power, the light adds together to create pure, blinding white light.
But paper doesn't emit light. Paper is dead. It just sits there waiting for ambient room light to hit it. So we can't use additive light. We have to use subtractive ink, CMYK.
Cyan, magenta, yellow, and key, which is black. These are the process colors. Ink acts as a filter. When white room light hits cyan ink, the ink absorbs or subtracts the red wavelengths and reflects the blue and green back to your eye.
If you mix cyan, magenta, and yellow ink together, theoretically they should absorb all light and give you pure black. But because physical ink is imperfect, mixing them actually just gives you a really ugly, muddy brown.
Which is why we need the K. The key color, pure black ink. It is added to the process to provide deep, true shadowings and crisp text.
But sometimes process color fails. CMYK is great for reproducing a photograph of a sunset, but what if you are printing the corporate logo for Home Depot? You need that exact, screaming, high visibility orange. CMYK mixed together can't get that vibrant.
In that case, you abandon process color and specify a match color or spot color. You look at a physical book of swatches and pick the exact orange you want.
But the universal language for this is the PMS, the Pantone Matching System. It's a patented catalog of thousands of exact ink recipes.
Instead of the press trying to fake the orange by printing tiny dots of magenta and yellow over each other, the pressman takes a literal bucket of custom-mixed, pure Pantone orange ink and pours it into the machine.
If you are printing a magazine with full-color photos, but you also need that pure Home Depot orange, you are running a fifth color job. It requires a massive press with 5 completely separate ink stations.
Conversely, if you are designing a cheap local newsletter, you might only use black and 1 Scott color. That's multicolor printing. Fewer than 4 colors, far less expensive to run.
Whether it's CMYK or Pantone, designers manipulate color using 3 dimensions. Hue is the actual color family. Is it red, green, or blue?
Saturation is the intensity or purity of that hue. A highly saturated red is the color of a fire engine. If you desaturate it, it becomes gray.
And value is the lightness or darkness. If you take a red hue and add black to it, you decrease the value, creating a shade, like maroon. If you add white to it, you increase the value, creating a tint, like pink.
And remember, standard process inks are transparent ink. They behave like stained glass. If you print a layer of translucent cyan ink and then print a layer of translucent yellow ink directly on top of it, the light passes through both, mixes in your eye, and you see green.
Okay, the design is done. The colors are translated. We enter the final stage of the digital realm, prepress.
Prepress is the highly technical bridge where the digital file is analyzed, trapped, color-corrected, and prepared for the violence of the press room.
When a designer finishes a file and promises it is flawless, it is declared camera-ready. It's an outdated term from when they used massive cameras to photograph the layouts, but today it just means the digital file is ready for output. The fully assembled file, with all its fonts and high-res images linked, is called the mechanical.
The most critical prepress task is imposition. This is the geometric puzzle of arranging the pages on a massive sheet of paper so that when that sheet is eventually folded and cut, the pages appear in the correct numerical order.
This requires entirely changing how you look at the document. A designer works in reader's spreads. On the screen, page 2 is sitting right next to page 3, exactly how the reader will see it.
But the printer must convert those into printer spreads. This is a completely different arrangement.
It's a mind-bending mental exercise. Take a single piece of paper, fold it in half like a greeting card. You have 4 pages. When you open it flat, what pages are printed on the outside? Page 4 is on the left and page 1 is on the right. They're printed right next to each other. On the inside, page 2 and page 3 are together.
Now imagine doing that math for a 64-page magazine printed on a single massive sheet of paper. Page 1 might be printed right next to page 64. Page 2 is next to 63. The imposition software calculates this incredibly complex geometry.
But the prepress software also has to account for the physical thickness of the paper itself. They use a mathematical adjustment called shingling, or stair-stepping.
Shingling compensates for creep. We'll see this physically in the bindery, but basically if you fold a thick stack of paper in half, the pages on the inside get pushed outward. If you don't adjust for this, the text on the inner pages will get chopped off. Prepress literally nudges the digital margins of the inner pages slightly toward the center fold, so they survive the final cut.
To verify this math, a printer will build a bulking dummy. They take the exact paper specified for the job, with no ink on it, fold it up, and physically measure how thick the spine is and exactly how much creep happens.
Once imposition and shingling are perfect, the digital file is sent to the RIP, raster image processor.
This is the heavy lifting. Ripping a file means a dedicated computer takes your beautiful, scalable vector math and converts it into a colossal, ultra-high-resolution bitmap. It calculates exactly where every single microscopic drop of ink needs to land on the metal plate.
The RIP sends those instructions to an image setter, a laser device that outputs the final film or directly etches the printing plate.
This etched plate is usually a thin sheet of flexible aluminum, treated so that the areas meant to print hold ink and the blank areas repel it.
But wait, before you authorize the creation of dozens of expensive metal plates, you must demand a proof. A physical or digital test sheet to ensure no disasters occur during the RIP process.
Historically, for a cheap layout, you'd get a blue line, also called a Dilux or brown line. It's a monochromatic, light-sensitive paper exposed to the film negatives. It doesn't show color, but it proves that all the text is there, no fonts crashed, and the pages are in the right order.
If you need to verify color, you ask for a color key or a chromalin. These are expensive, highly accurate proofs made from layering 4 colored films on top of each other.
Today, it's mostly digital. A printer will send a match print, a high-end digital proof that uses precisely calibrated toners to replicate what the press will do.
And if you are using that specific Pantone spot color, that Home Depot orange, you demand a drawdown. The printer actually mixes the wet ink, takes a piece of the exact paper you specified, and physically smears the ink onto it with a metal blade. You need to see exactly how the chemicals in the ink react to the clay on your specific paper.
So the proofs are signed, the plates are etched, but there is a massive logical gap here that we haven't explained. We said that a printing press only prints solid ink. A plate either deposits 100% cyan ink or 0% cyan ink. It is a binary machine.
Yes, there is no light cyan ink on the press.
So how on earth do we print a continuous tone photograph? How do we print a pale blue sky or the soft shadows on a face if we only have solid, harsh ink?
We rely on one of the greatest optical illusions ever invented, the halftone. We have to force the human eye to see the world in tiny dots.
A halftone is the mechanical process of taking a smooth photograph and shattering it into a microscopic grid of solid dots.
Think of it like a microscopic mosaic or Georges Seurat's pointillism paintings. The halftone dot is the individual unit of this illusion.
If you want to print a very dark gray shadow, the image setter etches huge, fat, black dots that are packed tightly together. They cover almost all the white paper. If you want a very light, pale gray, the machine etches tiny, pinpoint black dots spaced far apart.
Because the dots are so small, your human eye can't resolve them individually. Your brain artificially blends the solid black ink with the unprinted white paper and says, that area is pale gray.
It's essentially hacking the human visual cortex. And we measure the density of this dot grid in LPI, lines per inch. You might also hear it called screen ruling, line count, or screen frequency.
This is where your choice of paper canvas dictates your prepress math. If you are printing on cheap, porous newsprint, the wet ink is going to soak in and expand. If your dots are too small and too close together, they will bleed into each other, creating a solid, muddy mess.
So for newspaper, you must use a coarse screen. This is a halftone grid with less than 100 psi. The dots are large and spaced far apart to give the ink room to expand.
But if you are printing on that super calendared clay-coated paper, the ink sits perfectly still on the surface. You can use a fine screen, which is 100 pi, 150 pi, or even higher. The dots are microscopic, creating a photographic illusion with breathtaking detail.
But layering dots introduces a terrifying physical hazard. When you print a full-color photo, you're actually printing 4 separate grids of dots on top of each other. One grid for cyan, one for magenta, one for yellow, one for black.
If the geometry of those 4 grids isn't perfectly aligned, you trigger a moire.
The source Glossary has a terrifying picture of this. A moire is the result of wave interference. If the grids are slightly misaligned, the dots overlap and crash into each other in a repeating pattern. The resulting image looks like a dizzying, psychedelic plaid. It is completely ruined.
To prevent moire, prepress software mathematically rotates each color's dot grid to a highly specific angle. Black is usually set at 45 degrees, magenta at 75, cyan at 15, and yellow at 90. These specific angles create a microscopic rosette pattern where the dots nestle next to each other instead of crashing.
Designers also manipulate the image data before it's screened into dots. They evaluate the tonal range. This is the span between the absolute darkest shadow and the absolute brightest highlight in the photo.
A printing press has a much smaller tonal range than a glowing computer screen. It can't print absolute blinding white, and its blacks tend to muddy up.
So the designer has to perform tonal compression. They intentionally flatten the contrast of the image. They lighten the dark shadows so they don't fill in with ink and become featureless black blobs. And they darken the bright highlights so the halftones don't disappear entirely. They squash the image into a range the press can handle.
If the image has no color data, just black ink, it's a grayscale image.
But a simple grayscale image printed with just black ink can look a bit flat. To make it richer, you can print a duotone. This is a halftone image created using 2 ink colors. Usually you print one halftone grid in black to handle the deep shadows, and a second halftone grid in a warm gray or sepia to handle the midtones. It adds incredible cinematic depth to a black and white photo.
You can escalate that to a tritone using 3 colors, or a quadratone using 4. And crucially, a quadratone is usually 4 custom spot colors, not the standard CMYK. It is an extremely expensive technique used in high-end fine art books to reproduce charcoal drawings or vintage photography with breathtaking fidelity.
Sometimes you don't want the background of the photo at all. You just want the product floating on the page. You create a silhouette halftone, also known as an outline image.
To do this digitally, the designer draws a mathematical vector mask perfectly around the edges of the product. The mask acts like a digital stencil, blocking out the background and isolating the object.
And a final digital trick to make those halftones pop is unsharp masking. It sounds counterintuitive, but it's a software filter that actually makes an image look sharper. It analyzes the edges of the objects in the photo and artificially increases the contrast right on that border, tricking the eye into perceiving crisp focus.
All of this manipulation, all of this dot math, culminates in etching the plates. And the pre-press technician must check one last thing. They cannot send a wrong reading plate to the press.
A wrong reading plate means the image has been accidentally flipped backward. Since offset presses transfer the image twice from plate to blanket and blanket to paper, the image on the plate must be right reading, so it ends up right reading on the final paper. If you mess that up, the entire print run is backward.
The digital realm is complete. The files are perfect, the plates are etched with millions of microscopic rosettes. It is time to enter the roaring, ink-smelling, heavy machinery reality of the press room.
This is where abstract math collides with chemistry and sheer mechanical violence. There are several different technologies used to smash ink into paper, but the undisputed king of commercial printing is offset lithography.
It is the standard for a reason, and the chemistry behind lithography is beautifully simple. Oil and water do not mix.
Here's how it works. That flat aluminum printing plate has been etched. The areas where the image lives are chemically treated to be lipophilic. They attract oil. The blank areas of the plate are hydrophilic. They attract water.
The plate is wrapped around a spinning steel cylinder. First, it passes under water rollers. The water sticks to the blank areas but beads up and rolls off the image areas. Then it passes under the ink rollers. The petroleum-based ink is repelled by the wet areas but sticks perfectly to the dry, oil-loving image areas.
But the metal plate never touches the paper. That's why it's called offset. The metal plate presses against a second cylinder wrapped in a rubber blanket.
The blanket receives the wet ink image from the metal plate, and then the blanket rolls against the paper, transferring the image. Why? Because a soft rubber blanket conforms to the microscopic texture of the paper far better than a rigid metal plate ever could. It preserves the life of the plate and creates a flawless print.
There are older, more tactile methods too, like letterpress. This is how Gutenberg did it. You print from an inked, raised surface. The metal type physically smashes into the paper, leaving a deep, tactile indentation. It's slow and expensive, but highly sought after for luxury invitations.
The exact opposite of that is gravure, also known as intaglio. Instead of the image being raised, the image is etched into the metal cylinder, creating millions of microscopic wells.
The cylinder is flooded with highly fluid ink. Then a steel blade scrapes the surface completely clean, leaving ink only trapped inside the microscopic wells. The paper is pressed against the cylinder with immense pressure, literally sucking the ink out of the wells. Gravure is incredibly expensive to set up, but the cylinders never wear out. It's used for massive print runs, like millions of IKEA catalogs or printing currency.
If you are printing on plastic bags or corrugated cardboard boxes, you use flexography. It uses flexible rubber plates and fast-drying inks. It's essentially a massive, high-speed rubber stamp.
If you want to print a thick graphic on a t-shirt, use silkscreen or serigraphy. You push thick ink through a woven mesh stencil using a squeegee.
And for absolute, uncompromising luxury, there is engraving. The image is hand-cut into a copper or steel plate. It lays down a massive opaque layer of ink that is physically raised off the paper. You can run your thumb over an engraved letterhead and feel the letters standing up.
Because engraving is so expensive, people fake it using thermography.
The thermography is clever. You print the page with slow-drying ink. While the ink is still wet, you dust the whole page with a plastic resin powder. The powder only sticks to the wet ink. Then, you run the paper under an intense heater. The plastic powder instantly melts and puffs up, simulating the raised feel of engraving at a fraction of the cost.
We also have novelty printing, holography, which uses lasers to etch a three-dimensional light interference pattern into a metallic foil, which is then stamped onto the paper. Think of the security bird on a credit card.
Or lenticular printing. You print a sliced-up image and bond it beneath a sheet of plastic covered in tiny parallel lenses. As you tilt the card, the lenses show you different slices of the image, creating an animation or 3D effect.
Regardless of the printing method, the machines themselves are divided by how they eat paper. You have sheet-fed presses and web-fed presses.
A sheet-fed press takes pre-cut, individual sheets of paper, picks them up one by one with suction cups and fires them into the machine.
A web-fed press is a terrifying industrial beast. It doesn't use sheets. It uses a single, continuous, multi-ton roll of paper, the web that threads through the machine at highway speeds. Web presses are used for magazines and newspapers where volume is everything.
The speed of these machines is measured in IF, impressions per hour. A modern web press can easily hit 50,000 IF.
At those speeds, the paper isn't moving gently. It is being ripped through the machine by grippers. These are a row of metal fingers that physically bite down on the front edge of the paper and yank it through the cylinders.
And because the grippers have to hold the paper, they need space. This is the gripper edge. It's about a 3/8 of an inch strip at the leading edge of the paper where you absolutely cannot print any ink because the metal teeth are covering it.
As the paper flies through, it gets hit with ink. The ink lives in the ink fountain, a trough at the top of the press. A complex series of rollers pulls the highly viscous ink down, smoothing it out before it hits the plate.
The press operator stands at a massive console, constantly adjusting the flow of the fountain to maintain perfect density, the precise physical thickness of the ink film on the paper. Too much density, and the halftones turn into muddy blobs. Too little, and the image looks washed out.
Before the operator can run the job at 50,000 IF, they have to perform the make-ready. This is the highly skilled process of preparing the press. Filling the fountains, calibrating the suction feeders, aligning the plates. It can take hours and waste hundreds of sheets of paper.
And the absolute most critical part of the make-ready is achieving perfect register.
This is the alignment of the 4 color plates. The cyan, magenta, yellow, and black halftones must print perfectly on top of each other. If the magenta plate prints 0.5 millimeter to the left, the entire photograph becomes a blurry, color-shifted nightmare. The press is out of register.
To monitor this at high speeds, the plates include register marks. These are tiny target symbols, crosshairs printed outside the image area. If the press is in perfect register, the 4 colored crosshairs print exactly on top of each other, appearing as a single, crisp black cross.
The operator also uses a densitometer to scan the color bars, which are tiny squares of pure ink printed on the edge of the sheet, to ensure the ink density isn't drifting during the run.
But here is the brutal reality of the press room. Perfect register is a physical impossibility over a long print run. The paper stretches as it absorbs water. The metal plates heat up and expand. The grippers slip slightly.
This creates a massive problem for graphic designers. Let's say you design a layout with a bright yellow circle sitting directly against a dark blue background. That boundary where the colors touch is called a color break.
If the press shifts by a fraction of a millimeter, the yellow circle moves, and a tiny crescent of unprinted, glaring white paper is exposed between the yellow and the blue. It ruins the design.
To survive the physical reality of the press, pre-press uses a brilliant technique called a trap.
Trapping is intentionally printing one ink slightly over the edge of another ink. You create a microscopic overlap. So if the press shifts slightly, the overlap absorbs the movement and no white paper is exposed.
There are two ways to build a trap: a spread and a choke.
With a spread, you take the lighter foreground object, the yellow circle, and you digitally enlarge it by a fraction of a millimeter, so it spreads out and overlaps the darker blue background.
With a choke, you do the opposite. You take the dark blue background and you shrink the hole cut out for the yellow circle, tricking the background inward so it slides under the yellow ink. Either way, you've created a safety net of overlapping ink.
But when that ink overlaps on the press, it causes chemical issues. 4-color presses lay down all 4 inks in less than a second. The paper is getting hit with wet magenta ink directly on top of wet cyan ink.
That is wet trapping, and it is incredibly difficult to control. Imagine trying to paint a perfectly straight stripe of nail polish over a base coat of nail polish that is still completely wet. The inks want to mix, smear, and pull each other off the paper. It requires highly engineered ink viscosity called tack to work.
If the job demands absolute perfection, like a high-end metallic spot color, you might use dry trapping. You run the paper through the press, print the base colors, take the paper off the machine, wait a day for the ink to completely dry, and then run the paper through the press a second time to print the overlapping color. It is flawless, but highly expensive.
Sometimes you don't care about overlapping. You just want to cover the entire sheet in a solid color or a protective varnish. That is called a flood.
With all this violent speed, wet ink, paper dust, and water, things inevitably go wrong. The Glossary gives us a forensic vocabulary for bad printing.
My favorite is the hickey.
A hickey is infuriating. It happens when a microscopic speck of dried ink or a fleck of paper dust gets stuck to the rubber blanket. When it transfers ink to the paper, the dust blocks the ink, creating a solid spot surrounded by a tiny white halo. It looks like a tiny donut.
Then there is mottle. This goes back to our paper choice. If the paper has an uneven density, it absorbs the ink inconsistently. The resulting solid color looks cloudy, blotchy, and mottled.
Or scum, also called haze. If the chemical balance of oil and water on the lithographic plate gets compromised, the blank areas of the plate start attracting a tiny bit of ink. The white paper develops a dirty, thin haze of ink over the entire surface.
But the nemesis of every pre-press technician is dot gain, also known as press spread.
When the wet ink from the halftone dot hits the paper, it is instantly crushed by the metal cylinders. The physical pressure squishes the drop of ink, causing it to physically spread out and become larger than it was on the plate.
It's exactly like touching a wet marker to a paper towel. The ink bleeds outward. And if every dot in a photograph gains 15% in size, the entire photograph becomes dramatically darker, the shadows fill in, and you lose all your contrast. The text explicitly notes that uncoated porous papers cause massive dot gain compared to coated papers.
Which is why a paper's ink holdout is so important. High ink holdout means the paper resists absorbing the ink, forcing it to dry on the surface, keeping the halftone dots tight and crisp. Low ink holdout leads to dot gain and potentially show through, where the solvent in the ink soaks so deeply into the paper that you can see a ghost of the image on the reverse side.
Because all these perils, hickeys, model, out-of-registry sheets are guaranteed to happen during the maker-ready and the run, a printer always mandates an overrun.
This is a mathematically calculated surplus. If you order 10,000 brochures, the printer might actually print 11,000.
Because they have to account for spoilage. The hundreds of sheets thrown in the recycling bin while getting the press up to color. It is vastly cheaper to print an extra 10% while the machine is already running at full speed than it is to realize you are short 50 brochures and have to pay for a completely new maker-ready. The overrun lowers the unit cost, the total bill divided by the final number of acceptable pieces.
Let's talk about press efficiency. Most jobs are printed on both sides of the paper. How do we do that without making 2 sets of plates?
For sheet-fed presses, you use work and turn, or work and tumble. In work and turn, you put the front and the back of your brochure on the exact same printing plate. You run 1,000 sheets through the press. Then you take that stack, flip it over left to right, like turning a page in a book, and run the exact same sheets through the exact same press again.
Because you flipped it left to right, the front image prints on the back of the back image, and vice versa. Then you just cut the sheet in half, and you have 2 complete double-sided brochures. The key is that the gripper edge, the front edge of the paper, remains exactly the same.
If the layout requires it, you might use work and tumble. You run the sheet, but when you flip it, you tumble it top to bottom. The trailing edge of the paper now becomes the new gripper edge. It requires the paper to be cut absolutely perfectly square to work.
After the ink is laid down, whether turned or tumbled, the pressman takes the massive stacks of paper and begins jogging them.
They put the stack on a vibrating table that aggressively jostles the sheets until the edges align perfectly, creating a crisp, uniform, squared-off brick of paper.
The ink is drying, the piles are jogged, the press room is quiet.
But we don't have a product yet. We just have pallets of flat, oversized, confusingly arranged sheets of paper. How does this become a book?
We have to bring it all together. We are moving into the bindery, the land of blades, folds, and glue.
And the first rule of the bindery is that you cannot simply fold a thick piece of paper. If you take that heavy cover stock we chose in section 1 and force it in half, the wood fibers will violently snap. The clay coating will shatter. The dried ink will flake off. It looks like a jagged white lightning bolt running down your design.
To prevent that, you must first score the paper. A dull metal wheel presses deeply into the paper along the exact fold line. It crushes the fibers and creates a hinge, allowing the paper to fold cleanly and accurately without cracking.
Once scored, there are endless ways to fold a single sheet. The glossary lists the classics. The accordion fold, or fan fold. The paper zigs and zags back and forth, opening up exactly like the instrument.
The barrel fold, or roll fold. You fold the right panel in, then fold it over again, rolling the paper up inside itself to create 6 panels.
If you are making a standard greeting card, that's a French fold, you fold the sheet in half horizontally, then fold it in half again vertically. It creates a thick, luxurious 4-page card that is only printed on one side of the master sheet.
And for a dramatic reveal, the gatefold. The left and right edges of the paper fold inward so they meet perfectly in the center. Then the entire piece folds in half again along that center line. When the reader opens it, it unfolds like a set of grand double doors.
But folding a single brochure is easy. If we are making our 200-page annual report, we are dealing with signatures, also called forms.
This is the culmination of that printer spread math we did in pre-press. A signature is a single massive sheet of printed paper that has been folded in half and in half again and in half again until it forms a thick booklet.
Because of the imposition math, once you fold that sheet down, all 16 pages are suddenly in perfect reading order. A book is just a collection of these 16-page or 32-page signatures bound together.
There are 2 ways to assemble these signatures into a book. Gathered signatures are simply stacked side by side. Signature A is placed next to the signature B, next to signature C, building the thickness of the spine.
Nested signatures are completely different. You take signature A, open it to the middle, and drop signature B directly inside of it.
And this is where the pre-press concept of creep comes back to haunt us with a vengeance.
Yes. If you nest 5 thick signatures inside each other, the physical bulk of the paper around the fold pushes the inner pages outward. The middle pages literally stick out further than the cover.
When the bindery clamps that book down and drops a guillotine blade to trim the outer edge flat, what happens?
The blade slices off more of the inner pages than the outer pages. If pre-press didn't use shingling to mathematically move the inner text away from the edge, that guillotine blade slices right through the typography. Half the words on the middle pages are gone. It is a catastrophic, unfixable failure. The physical reality of paper thickness destroys the digital design.
It is the perfect example of why designers must understand manufacturing. Assuming the creep was handled, how do we attach these signatures together? We have several binding methods.
If you gathered the signatures side by side, you almost always use perfect binding. The bindery clamps the stack of signatures together, uses a rough grinder to completely mill off the folded spine, creating a rough surface of loose fibers, and then floods that edge with hot, flexible adhesive before wrapping the cover around it. Look at any paperback novel or thick magazine like Vogue. That flat, glued spine is perfect binding.
If you are making a high-end hardcover book, you use case bind. The signatures are sewn or glued together and then attached to a rigid case made of heavy binder board that has been wrapped in cloth, leather, or paper.
If you nested the signatures inside each other, like a comic book or a thin catalog, you use saddle stitch. The nested pages are draped over a metal saddle, and heavy wire staples are driven straight through the center fold. It's incredibly cheap and allows the book to lay completely flat.
But if the book gets too thick, a staple can't reach through the center fold. In that case, you might side stitch or side wire. You stack the pages and drive staples straight down through the top of the entire stack near the left edge. It's incredibly strong, but the book will violently refuse to lay flat when opened.
For manuals or cookbooks that must lay flat, we lose mechanical bindings. Comb binding punches rectangular holes along the edge and inserts a flexible plastic comb that curls in on itself.
Wire-O binding is the premium version of that. It punches square holes and inserts a continuous double-loop metal wire. It's highly durable and looks very professional.
And for thick architectural portfolios or restaurant menus, screw and post binding. You drill a literal hole through the stack of paper, push a threaded metal post through the back, and screw metal cap onto the front. The beauty is you can unscrew it to add or remove pages later.
The book is bound, but it might need finishing to protect the ink or elevate the tactile experience. Some finishes are applied in line,
meaning the finishing happens directly on the printing press at 50,000 sheets an hour as the last step before the paper comes out.
The most common inline finish is a varnish. It is essentially clear ink. It can be glossy or dull, applied universally over the whole sheet to seal the ink, or applied as a spot varnish just over the photographs to make them pop against dull text.
If a varnish isn't tough enough, you upgrade to an aqueous coating. This is a water-based polymer. Because it's water-based, it dries incredibly fast and provides a much thicker, more scuff-resistant layer than varnish. It prevents fingerprints from ruining dark ink.
But the absolute hardest, most durable armor you can put on paper is UV coating, ultraviolet coating. It is a thick, liquid plastic rolled onto the paper and instantly blasted with high-intensity ultraviolet light. The UV radiation causes a chemical cross-linking reaction, instantly curing the liquid into a rock-hard, ultra-glossy plastic shell.
If you are making a restaurant menu that needs to survive spilled wine, you bypass coatings and use a laminate. A machine uses high heat and immense pressure to melt a solid sheet of plastic film directly into the fibers of the paper. It is practically indestructible.
Sometimes, finishing requires structural changes to the paper that the bindery can't handle. The job is sent to a converter.
Converters are specialized manufacturing plants. They don't print. They transform flat-printed sheets into three-dimensional objects: bags, boxes, envelopes.
To do this, they use a die. A die is like a heavy-duty cookie cutter. It's a wooden board with razor-sharp steel rules hammered into it, bent in the exact shape of the flattened box.
The press smashes the die into the paper with tons of pressure, creating a die cut, a clean structural cut entirely through the paper.
Or if they're making sheets of stickers, they use a kiss die cut. The razor blades are calibrated with microscopic precision to slice through the top layer of sticker paper, but stop short of cutting the waxy backing paper underneath. It kisses the backing, allowing you to easily peel the sticker off.
Converters also alter the topography of the paper. They can create an emboss. The paper is placed between two interlocking metal dies, one raised, one recessed. The press crushes them together, permanently forcing the paper fibers to stretch upward, creating a raised, tactile 3D shape.
And the inverse is a deboss. The metal die pushes the design deeply down into the thick paper, creating a recessed trench.
If you want that deboss to shine, you use a foil stamp. You place a roll of microscopically thin metallic film, gold, silver, holographic, between a heated metal die and the paper. The heat melts the adhesive on the back of the foil, permanently fusing the metal film into the paper in the exact shape of the die. It is the ultimate signal of premium luxury.
Finally, if the printed piece is a 3D product, the converter handles the packaging.
The glossary covers the basics. A tray is a shallow folding carton with a hinged bottom, like the cardboard box carrying a flat of soda cans. A tube is a rectangular sleeve glued on one edge. You fold the ends in to close it, like a toothpaste box.
For small retail items, they might use a blister pack, a printed cardboard backing with a clear, vacuum-formed plastic dome glued to the front, trapping the product inside so the consumer can see it but not touch it.
Or simply shrink wrap, wrapping the finished stack of books or products in a loose plastic film and passing it through a heat tunnel. The heat causes the plastic polymers to violently contract, creating a tight, protective, tamper-evident seal.
The manufacturing journey is finally over. The glossy, perfectly bound, UV-coated, shrink-wrapped piece is sitting on a loading dock.
But the life cycle isn't complete. A printed piece is utterly useless if it just sits in a warehouse. It has to go out into the world. It must fulfill its purpose with an audience.
And here is the reality. Every single agonizing decision we just discussed, the 100-pound coated cover stock, the asymmetric grid, the 5-color Pantone press run, the costly UV coating, all of it was dictated by the target audience.
Before the designer even sketched an idea, the marketing team provided demographics, cold, statistical data about the target consumers, their age, gender, geographic location, median income, family size.
But demographics only tell you who someone is. To design effectively, they relied on psychographics. This attempts to map the psychological profiles, the internal motivating factors, the values, and the lifestyle choices of those demographic groups.
They likely supplemented this with observational research, literally watching subjects interact with packaging or mailers in their natural environments. Do they struggle to open the blister pack? Do they throw the envelope away without looking at it?
Based on all that data, the company determined exactly what kind of physical object was needed. It is broadly called collateral, any ancillary printed material used to support a sales effort or advertising campaign.
Our massive annual report is collateral. But it could have been a simple flyer, a cheap single-sheet handbill run on a coarse screen, or a newsletter, a serialized publication sharing internal company information.
Because our piece was highly targeted, it falls under direct mail. Advertising that bypasses mass media entirely and uses the postal system to place a physical object directly into the hands of a specific individual.
Getting millions of physical objects through the postal system efficiently requires designers to surrender some of their pristine layouts to functional, machine-readable marks. Have you ever looked at the top right edge of a business reply envelope and wondered what those weird vertical barcode lines are?
Those are FEMs, facing identification marks.
The Glossary explicitly defines the FEM as a machine-detectable series of vertical bars. When the envelope hits the postal sorting machine at 30,000 pieces an hour, optical sensors look for that FEM. It instantly tells the machine which way the envelope is facing, allowing machinery to automatically orient it, cancel the stamp, and route it without human intervention.
Right next to the FEM, sitting where the stamp would normally be, is the indicia.
An indicia is a printed box containing specific text. It proves to the postal system that postage has been prepaid in bulk by the sender. It displays the permit number and the exact mailing classification. Without it, the direct mail campaign goes absolutely nowhere.
And at the very bottom of the envelope, you'll find the barcode, a specific series of parallel lines that a laser scanner translates into the exact routing ZIP code, allowing the mail to be sorted down to the individual mail carrier's walking route.
Sometimes a designer wants to avoid printing addresses directly onto the envelope. They will design a window envelope. A die-cut hole is made in the front of the envelope, covered with clear plastic. The designer has to meticulously align the folded letter inside so that the recipient's address shows perfectly through the window.
And what is the ultimate goal of this direct mail piece navigating the postal system? To establish identity, to build trust.
The piece exists to place the brand in the consumer's hand. The entire design anchors around the company's logo, a unique, legally protected visual design or symbol that instantly communicates the brand's identity.
It might specifically be a logo type. A logo that doesn't use a symbol, but relies entirely on a custom, unique typographic treatment of the company's name. Think of the flowing script of Coca-Cola or the bold geometry of FedEx.
That logo is fiercely protected as a trademark, a legally registered identifier. The company will go to immense lengths to ensure that trademark is never distorted.
Which is why the industry relies on universal standards like SWOP, specifications for web offset publications. SWOP dictates exact color profiles, ink densities, and dot gain tolerances. It ensures that the red in the Coca-Cola logo looks exactly the same, whether it is printed in a magazine in New York, a billboard in London, or a direct mail piece in Tokyo.
Sometimes, a massive national brand will print millions of gorgeous 5-color brochures but leave a small blank white box on the back cover. They send these shells to local independent dealers who will then run them through a cheap local press to imprint them. They add their own local address and phone number over the blank space.
And with that, the journey is complete. The piece has navigated the digital math, survived the violence of the press room, cleared the postal system, and arrived in the hands of the reader. The life cycle from abstract thought to physical reality is done.
It is truly staggering when you zoom out and look at the sheer scale of the engineering required for something we treat as disposable. The next time you pull a piece of printed mail out of your mailbox or pick up a cereal box, I want you to stop and look incredibly closely at it. You are not just holding paper. You are holding a physical record of thousands of agonizing, microscopic decisions.
You are looking at the legacy of basis weight calculations and opacity choices. You are seeing the invisible, rigid math of grids, flow lines, and kerning. You are holding the optical illusion of CMYK halftones.
You are feeling the results of wet trapping, the chemical balance of offset blankets, the the terrifying geometry of nested signatures, and the indestructible heat of UV coating.
It is a miracle of heavy manufacturing hiding in plain sight.
It really is. Now, as we wrap up, I want to pull on a thread that we've been dancing around this whole time. A final thought to leave you with. We spent this entire deep dive exploring the physical constraints of manufacturing, but we live in an increasingly aggressively digital world. We are moving toward VR, the metaverse, purely screen-based, pixel-driven lives.
And yet, look at the aesthetic choices digital designers are making today. Look at what they spend all their time programming.
What do you mean?
Digital design is currently obsessed with mimicking the exact physical flaws and imperfections we just spent an hour trying to solve in the press room.
Oh, wow. You are completely right.
Think about it. An app developer will write complex code to add fake dot gain and halftone patterns to a digital photograph, just to make it look authentically vintage.
Or they apply a filter that intentionally introduces the catastrophic moire pattern we said ruins print jobs.
Exactly. They build digital pages with artificial decal edges to fake the look of handmade paper. They design digital buttons with drop shadows and inner glows to simulate a tactile deboss. We have screens capable of infinite scalable vector perfection, and we use that processing power to render the flaws of heavy machinery.
It is the ultimate skeuomorphism. Why are we so desperate to drag the ghosts of physical printing into the digital future? Even when we completely escape the constraints of ink, paper, and metal plates, we intentionally program the accidents of the bindery back into our glowing screens.
It suggests something profound about human psychology. We inherently distrust flawless digital perfection. It feels sterile. We crave the physical weight, the texture, the friction, the reality of the printed word. The language of print is so deeply embedded in our collective consciousness that a visual world without its flaws feels fundamentally fake.
That is an incredible insight. We don't just want the information, we want the evidence of the labor it took to create it. Well, thank you so much for joining us on this deep dive into the hidden language of design and manufacturing. If you enjoyed putting on the X-ray glasses and seeing the invisible architecture of the physical world, please hit that subscribe button.
And keep looking closely at the ordinary objects you hold every day.
Yeah.
There is an entire universe of engineering right in your hands.
Absolutely. And as a final reminder, if you want to hold a physical masterclass in this vocabulary, complete with the incredible visuals and diagrams we referenced today, scan the QR code on your screen right now, or click the book link directly below in the description to grab your own physical copy of the Graphic Design Reference Plus Specification book. You will never look at a magazine the same way again. Until next time, keep diving deep.